Give us his third lecture.
Good morning. So what I'd like to tell you about today is deconfinement in pure gauge theory. This is an outline of my talk, and at least at the beginning, I'd like to describe to you what the order parameter is in a pure gauge theory, and really what it means to have deconfinement. This is something that, particularly for the experimentalist, you've probably heard about in some form, and I hope you at least get a basic idea of what's going on, because it really is fundamental. And the idea is that there's, in a local gauge theory, there's a hidden global symmetry. So, in a non-abelian gauge theory, the transformation of the gauge field is somewhat complicated. It's really a matter of a redundant degrees of freedom that we have. At this, you can take an arbitrary matrix, an SU3 matrix, and change it at each point in space-time. That's such a complicated thing. But let me consider the simplest possible gauge transformation that you could imagine. That is, at each point in space-time, I make it the same gauge transformation. So this funny derivative term here doesn't enter. And all I have is the gauge transformation on the right side and the Hermitian conjugate on the left side. Well, that's the simplest thing you could do, and this is always there. This is like just rotating what you mean by red, green, or blue color. Well, let me consider then an even simpler thing. This gauge transformation has to be an SU3 matrix. That means its determinant has to be equal to 1. If its determinant wasn't 1, then we would have a U1 gauge theory. So one way that I can do this is I can take a diagonal matrix where each element is a third root of unity. That is, it's e to the 2 pi I over 3. And if I do that, then the determinant is the product of these three matrices, and since it's the third root of unity, it's going to be equal to 1. That is, e to the 2 pi I over 3 to the third power is obviously e to the 2 pi I or 1. Okay, fine, so what? Well, the point is that it's this third root of unity, the space, times the unit matrix. And this is what's so important in what enters. Because omega, this gauge transformation, which I'll now denote as omega 1, is proportional to the unit matrix, then think of how the gauge potential transforms. Well, on the left-hand side, I get e to the minus 2 pi I over 3. On the right-hand side, I get e to the 2 pi I over 3. But it's proportional to the unit matrix, so this whole thing is invariant. That appears to be a completely trivial matter, except for the fact that consider how quarks transform. Quarks transform for a local gauge transformation, like this matrix over here. And if I take this to be a constant, all that changes is that I have phase. So quarks transform non-trivially. And what this means is that in a pure gauge theory, if I don't have dynamical quarks, that there's a global Z3 symmetry hidden in SU3. Now, it's Z3 because I have three possible roots of unity. I can have either the 2 pi I over 3, either the 4 pi I over 3, or either the 6 pi I over 3, which is equal to 1. And so it shows us that without quarks, an absolute measure of confinement or deconfinement is related to this symmetry. And the question then is, and it's a dynamical question with quarks, is this a good approximation or a bad approximation? Is the Z3 symmetry badly broken or only approximate? And if I can take my a second, Huff came up with this in, I believe, 78, when I was a young graduate student like yourselves, and I remember a very distinguished mathematical physicist, Barry Simon, saying, this couldn't possibly have anything to do with deconfinement because it was mathematically trivial. And so it shows you that sometimes mathematically trivial structures can actually be rather non-trivial physically. Okay. We can then consider, now I'm going to assume you have some knowledge of finite temperature. So here, the y-axis is denoting imaginary time that goes from 0 to 1 over the temperature. And we can take a Wilson line that runs up in the imaginary time direction. This is the path under exponential of e to the IG times the vector potential. This is like the propagator of an infinitely heavy test quark. As a Wilson line under a gauge transformation, it's not obvious, but it transforms like one gauge transformation at the beginning, that's what makes it form x and tau equals 0. And then like the complex conjugate at the other end, at x and 1 over the temperature. And because of this change, what we can do is we can make this gauge transformation at the top differ from that on the bottom by one of these Z3 gauge transformations. That won't change gluons because, as we showed on the previous transparency, gluons are invariant under these Z3 transformations. But if we take this Wilson line in the fundamental representation, it transforms by this phase factor. And this is known as the Polyakov-Susskind rule. So it's gauge invariant under local gauge transformations, but under the global gauge transformation, it transforms by one of these factors of Z3. Now, at this point, you really might think, oh, come on, this is just some trick of the Euclidean time or something. But I would like you to understand, and this is the one slide I hope you get out of the whole talk. If you fall asleep after this, that's fine with me. It won't bother me at all. But I want you to think about, I mean, typically what people say is, oh, confinement, it's due to some infinite mass and whatnot, and it's not. It's not due to an infinite mass. What it's due to is the following. That in the vacuum, you have different domains, and they all have different phases. I don't know what the structure of these domains is, it's complicated. But you have domains where this global phase factor is 1 where it's e to the 2 pi I over 3, and one where it's e to the minus 2 pi I over 3. So one way of drawing this is 1, this is e to the 2 pi I over 3, and this is e to the minus 2 pi I over 3. These are the 3 roots of unity. And then what happens is the propagator, a test particle, goes through the vacuum, and it picks up these phases in an arbitrary manner. Sometimes it's this, sometimes it's that, sometimes it's that, with equal probability. And so what you have is, the propagator is non-trivial in each of these phases, but the phases, it's easy to see that if you add them together, it's 0. And this is what confinement is. It's this 0, this random phases bouncing back and forth. And so confinement is not this infinitely heavy effective mass, but it's this phase decoherence. And in fact, it's very similar to the phenomenon of Anderson localization, where a particle propagating through a medium that picks up an arbitrary phase scattering off of impurities. And in fact, you can show that as you go to SUN theories, that you always get the n roots of unity, and in the confined phase, you have a deconfinement in a similar manner. In fact, at infinite n, if I hopefully get to it, the uniform distribution of eigenvalues that fills up the entire unit circle. Yes?
So this works for quarks, but gluons are also confined. That's the similar mechanism.
This works for test quarks.
Okay.
I haven't. Yeah, it doesn't tell you right what happens with gluons. Yeah.
But can then want to cut a similar argument for gluons?
That's a very good question. What happens there is you have to take this A naught, you can define a Wilson line in the adjoint representation. That's what you'd want to do. And in that case, you find this loop would be invariant under that symmetry. So you might say, whoa, well then we don't have an absolute measure of confinement for adjoint sources such as gluons. But the lattice indicates that in the confined phase, to a very good approximation, you do have a measure of confinement. But that's a non-trivial result, and I don't know if I have that here. Remind me again at the end of the talk when I show some lattice data. But that's a very good question. It doesn't work, obviously, for gluons.
Question. Can I get co-confined potential as a function of the polynomial loop?
Sure, from the two-point function of the loop confined loop. That will show a string tension in the confinement phase. Yeah. Okay, so what you have is at zero temperature, I've shown the expectation value of the polycloth will vanishes. So this is a plot of the expectation value versus temperature. In contrast, at high temperature, the perturbative fluctuations should be small. The coupling runs like 1 over the logarithm of the temperature. The fluctuations in and out should be small. So eventually the loop should go to 1. So you have two phases between a confining phase where the loop is strictly 0, without dynamic purport, I should stress again, and one where it's non-zero. And here I indicate what you expect the behavior to be like. And for 3 colors, we expect it to be first order. And the reason is simply because I'm just going to mumble the words, but hopefully from the first lecture. The point is Z3, there's a cubic invariant, because it's a 3. And because of the cubic invariant, as shown by Svetitsky and Yaffe, from the Z3 symmetry, you expect this to be a first order transition. In fact, it turns out to be first order from numerical simulations of the lattice for any number of colors bigger than or equal to 3. But that's a non-trivial result. Okay. Let me then go on to consider a simple example. And here I'm going to show you, this is the first part I hope everybody got to some extent. The confinement is with the Z3 symmetry. Now I'm going to give you a simple example that's nevertheless illuminating. And that is, consider a classical field where now I'm going to concentrate on SU3. This is one of the SU3 matrices. It's 1, 1, minus 2. And I'm going to take a very particular choice for a classical field. And then when I compute this, what I can show is, if I take this Q here to be 1, 2, or 3, notice there's a 2 pi t over 3 times Q. And what I'm going to get is, if you work it out, you can see this is such that I'm going to get one of these third roots of U. It's not too hard to see. Now you might say, okay, fine, that's trivial. Well, what if I consider an arbitrary constant Q? This is some background field. I can compute the field strength tensor. But look, I'm going to take Q to be constant. So the derivatives here vanish. So this part doesn't contribute. And it's a diagonal matrix. So it commutes with itself. So then this would seem to tell me that if I take any one of these fields, that it's a vacuum. And that can't be right. There should only be 3 vacua. I argue that there's only this Z3 symmetry, and this can't be the right vacuum. And what I'm going to show you now, how this degeneracy at the classical level is lifted by quantum effects. So what I'm going to do, and again, this is very useful for a theorist to compute, is use a background field method. What that means is I'm going to take that previous field, consider it as a classical field, and expand to one loop order about quantum fluctuations. When you do that, you have to expand to quadratic order, you have to choose some gauge. It turns out that the result you get is independent of the gauge. That's not obvious. and you just get trace log of b squared, where this is the propagator in this background field. Now, normally when you do a background field calculation, such as about an instant time, this is a very complicated thing, and it's really hard to work out. In this case, because it's a constant field, it's really, really easy. So, what is this thing? Well, d mu classical acting on some quantum fluctuation, well, it's the ordinary derivative, and then there's a commutator term, because this is another real engagement. I have to compute it at non-zero temperature, so my time derivatives are, give me factors of 2 pi t times an integer, and similarly, the integral over k naught is a sum. The problem becomes, how do I deal with this commutator between the classical field and this quantum fluctuation? Remember, this is a non-trivial matrix. It's not, it's diagonal, but it's non-trivial. And the answer is, I use a ladder generator analogous to those for SU2. These are two of the ladder generators. There's another one where this is one, or one here. They're nice because the square of any ladder generator is 1, and the only thing that's not zero in the trace is between the plus ladder generator and the minus. It's also nice because the commutator, and you can sit down and work this out, it's really trivial. The commutator between one of these ladder generators and this particular diagonal matrix gives you back the ladder generator. So what that means is, we want to evaluate this commutator. This commutator is the time derivative plus the commutator. That if I take these ladder generators, what I'm going to get is I'm going to get the same thing back. I don't have any mixing between different components. And in fact, I've chosen my normalization such that instead of getting 2 pi t times an integer, as I would in free field theory, I just get 2 pi t times an integer plus this extra factor q, which is now just a constant. So I can then work out, very simply, what this potential is. It's just a trace law, and it looks exactly like a free particle, except the energies excuse me, are shifted by this vector q. Okay, so let me assume that this q is a constant, because then it's really easy to work out. And typically, if you have something like this, if you have a trace law, the first thing that you should do is differentiate to get something similar. So I differentiate. What am I going to get? This is like, I'm going to get a factor of the momentum times a propagator. But these are all constants. I've just shifted P naught, and it's actually easy to see. This is what the integral is, what this trace is here. There's an integral of d3p times this shifted energy divided by a propagator. And what I can do is I can just do this integral over the momentum. Usually you're used to, at finite temperature, first you do the sum, then you do the integral. Here it's better to first do the integral, then do the sum. So you do that, and you see, well, I have d3p over p squared, so what I'm going to get is one factor of this momentum, and in fact it's going to be absolute value. So this is going to give me this absolute value of n plus q. And then this factor here, this p naught plus, is again n plus q. So this is the sum that I want to evaluate from n equals minus infinity to infinity. Now you might worry, this is kind of a divergent sum. It's sum on n squared. But mathematicians are very clever people, and they tell us this is just a form of zeta function. This is the definition of the zeta function. It's the sum of n from 1 to infinity, 1 over n plus q to some power, r. And so in fact, you can write this sum over all n as a difference of zeta functions. So the reason you have a difference is this sum is coming from n equals 1 to infinity, and this of 1 minus q is coming from the sum over negative n's. And in fact, the point is mathematicians have shown that except for r equals 1, that this is you can define this sum by analytic configuration. Well, clearly, I'm just pulling a rabbit out of a hat. You have to work this out, but the point is that this zeta function of -2 is derivative of something very simple, of this q squared times 1 minus q squared. And remember, I took a derivative here in order to get this sum, so I can integrate that, and what I find is I get a potential that's just a number times t to the 4th times q squared times 1 minus q squared. And this is very nice because it then shows, remember I argued that classically everything was degenerate, and I've lifted that degeneracy. So this is what the potential looks like from q equals 1 to 3. In fact, you have to be careful. This is only defined for q modulo 1 absolute value. But what it shows is for q equals 1 or 2, these are the Z3 vacua. Then I've lifted the degeneracy from quantum effects, and I now have 3 degenerate vacua. Q equals 0 and 3 are the same because the Wilson line equals 1 in either case. But 1 and 2 are these non-trivial Z3 vacua, and this is the Z3 sum. I should also say that this potential is non-trivial. There's the potential for the pressure of gluons hidden in the zero of this potential, but that's not going to enter for the following case. So this is very nice. We had a potential, we lifted the degeneracy, and then we can ask about the following problem. We can ask, well, I could consider a kind of tunneling problem. I could consider tunneling, this is a valid vacuum, this is a valid vacuum, but they're different vacua. The Z3 phases are different. So we can consider an interface tension. We can consider a box that's long in one dimension. We can have the Wilson line equal to 1 at one end of the box and 2 pi I over 3 at the other end of the box, and tunnel between these two vacua. And we can, in fact, use the potential on the previous slide to compute this interface tension in weak coupling. So what are we going to get? Well, we have the usual, see, what happens is here, we have this background field that depended upon Q. Now we're going to have to let this Q be spatially dependent. So there's a bit of a swindle here, and I'll explain to you shortly why it's correct. So now when I take the field strength tension at the classical level, I am going to get something non-trivial. I'm going to get something A naught is 1 over G. So the derivative of A naught ddz of A naught squared is going to give me 1 over G squared. And then I'm going to get this derivative of Q in the Z direction. And then I'm going to get the potential that I had before. Now the potential, because A naught was 1 over G, and it's G times A naught with the covariant derivative, there's no G here. So this is of order 1. And in fact, what you can show is you can balance a term that's 1 over G squared, that's the classical level, the quantum potential, which has no G's in it, and what I'm going to get is a factor after rescaling Z that's 1 over the square root of G squared. So it's a tunneling problem, like an instanton, but unlike an instanton, the action isn't 1 over G squared, it's 1 over the square root of G squared. And you can in fact show that if you balance the classical action and this quantum potential, that you can find a minimum, and this is the value that we get for this kind of potential. Now, the swindle that I've done is that I've assumed Q is slowly varying, but that's valid because of what basically is going to happen is that this interface is going to be large. It's going to be 1 over GT. The scale, the fluctuations that determine the potential are on the order of 1 over T. That's a small distance. And the scale of the interface is broad. It's 1 over GT. So if G is small, this should be a valid approximation. So this is fine in weak coupling, and in fact, lattice simulations have shown that this works pretty well down to temperatures above 10 TC. This is results by Cortizantes, Kavner, and this is by Bursa and Pepper. And what you can show is that the lattice result compared to the semi-classical, this is the temperature axis, this is the semi-classical, that it works very well at high temperatures, and then of course it fails near TC, and I'll show you later how you can treat this region near TC. But I just wanted to show you this example, because in fact it turns out it's not only useful for computing this tunneling problem, but it will become useful in terms of developing an effective theory near TC.
Well, good. What is this lambda ms?
On the lattice, you have to define what the renormalization mass scale is, and that's the renormalization mass scale.
How large is?
But typically in pure gauge, it's about 300 MeV. With dynamically quarks, it's about 225, something like that.
Could you please explain once again what is this lattice data showing? What is
It's the ratio of this interface tension to the semi-classical result. So if this is near 1, the semi-classical result is working. So notice this temperature is some ridiculous scale, where TC is here, and it's only working for large temperatures, but it was a semi-classical calculation, so it should only work for weak coupling at high temperatures.
But can I mean this G which you have in your formula, okay, from this semi-classical results, of course it's temperature dependent. Have you included this temperature dependence of G when comparing to?
I believe they included the two-loop bound.
Okay.
But again, remember, this is an exponential scale in temperature, so this result was not that impressive.
May I ask, when you introduce the background field proportional to the generator T8?
Yeah.
I mean, as you see, you have these two generators in the Karpacz algebra, T3
Yes.
and T8. Why can we ignore the field in the T3 direction?
Because I'm looking at just the Z3. I'll shortly introduce the other generator to look at deconfinement. And in fact, near TC, you have to include that direction.
Right, because the period of potential has its minimum both at high and low temperatures on the axis where you can...
And I'll include that later.
Okay.
I will include that. This is just a simple example to show how to use background field, but that will enter later, absolutely. Thanks for
No, I have some remark concerning your critiques. Exactly this series which you have in the last is obviously divergent, and there is no discussion about it. Yeah, it's obviously divergent. And then what you mentioned, the mathematicians are clever. I wouldn't say this because there are no mathematicians who would agree that the procedure you use is a valid one. I would say quite opposite. Physicists are smart with dirty tricks, yeah, because that's what you got was a dirty trick, but it doesn't mean that it's a true answer, because divergent series is just divergent series. So if you group points of this series, then you can get any answer, whatever you wish. So it's unacceptable from the mathematical point of view.
Look, we don't use this micro, okay? Because
Okay.
I'm still speaking, so
Without microphone.
it's dangerous.
One can evaluate the series. I was
No,
lit.
this expression is divergent and point and nothing else. If you have, for example, very simple example, you have alternative series. +1, -1, +1, -1, and you sum over this, you can get, with this kind of grid, you can get any answer from 0, 1, 10, whatever you wish.
Well, okay, no. So let's ask the students a problem. What's 1 + 2 + 3 and so on?
Yeah, exactly.
It's minus pi squared over 12.
Yeah, of course, one can do it, but
No, it's a well-defined answer. It's minus pi squared over 12.
no.
1 plus 2 plus 3.
The only answer is.
This is our homework problem. Evaluate 1 plus 2 plus 3 plus 4. Up to
No
infinity.
way. If you have infinity minus infinity, it's always a matter. There is no final answer. Only.
But the proof of that is not that
It's nothing to prove.
Okay, now this looks like that this is better discussion for the exercise session.
That's all, but I declare the technical serious and this end of this discussion.
Yeah, so let's drop this later.
We like that approach.
Rather continue.
We love zeta.
We love it.
We love zeta.
We love it.
Zeta functions are wonderful things.
Exactly.
And
Okay, guys, silence please. One discussion in time.
so there's no mathematicians here to object that they are in fact much smarter than we are. I disagree upon that point. I think they're much smarter. We're just clever at ignoring the problems that they worry about. Okay, so let's go on to look at what the result, and this is data that Olaf Kaczmarek did with Gupta and Butner about 10 years ago. I think it's definitive state. This is data from the lattice for the normalized triplet loop. And this is SU3, no quarks. So this is the deconfinement temperature. So it's the sort of parameter strictly. It jumps to a value of about 0.4 APC. And then this is to a value that is approaches 1, it's approximately constant from 4 times the deconfining temperature. What this temperature is you have to define how to define the mass, understand how to define the mass scales. It's about 260 MeV. Although Olaf, if he's here, may disagree. But about 260. Is that correct, Olaf?
Yeah.
Something like that. Now, and to answer, somebody asked about what about gluons. If you ask gluons, not the renormalized triplet loop, but the renormalized octet loop, so something that is not invariant under Z3. I don't have that data here, but what you will find is it will jump to a value, I believe it's about 0.2, and then it jumps to a very small value. So it's non-zero, but it's a very small value. So gluons are not strictly confined, but that appears to be approximate. So.
Question. Some professors and also students have a problem because this Polyakov loop is the character of the fundamental representation. Thus, according to group theory, never be larger than unity.
For the bare quantity. The bare quantity is always less than 1. When you look on the lattice, this vanishes exponentially, like e to the minus the number of time steps. And the bare quantity on the lattice is always less than 1. If you look at a renormalized quantity after subtraction, then, as is true of, say, phi squared in a gauge theory, in a scalar theory, which you say is positive. Once you subtract it, then you no longer have positivity of the subtracted quantity. And similarly, you can show that this approaches 1 from above
I know. But,
because of renormalization.
But this is really a surprise for me always when I see it. A complete surprise.
Shuriak claims he understands it completely, but I don't
Really? Okay.
Okay. You can also calculate this potential with quarks, and what you can show, I won't go through the calculation, I'll leave it as a problem, is that the Z3 symmetry is broken by quarks, so these are the Z3 degenerate factor. With quarks, we no longer have that. Q equals 0 and 3 are the same because the Wilson line is equal to 1. And so this dynamical symmetry is broken. And you see that in the values of the Polyakov loop. This is again the normalized Polyakov loop with, using Lucier flow, which is a very elegant analysis. This is with 2 + 1 flavors. The chiral transition now occurs at a temperature of 155 MeV, and you see that the value of the polytope group is extremely small. And this, I will argue, is a real problem for understanding the value of this quantity. There's a broad region going up to about 600 MeV of where this polytope group is significantly less than 1. And if you would take this at face value, this would indicate that you're in what I would call a partially deconfined phase, a semi-quark-gluon plasma in an extremely broad region. And one of the principal things that I'll discuss in my last lecture is that if you look at other quantities, in particular quark fluctuation, you would think you are in an approximately perturbative region already by 200. But there's clearly some region in which you have a partially deconfined phase, and this is going to be the subject of my shortly. I forgot. In answer to the question about adjoint loops, in fact, you can show this was first shown by Olaf Kaczmarek and collaborators that the value of the normalized loop scaled by an appropriate power of the Casimir is approximately constant. It kind of breaks down near TC, but Pisarski and Shadler showed this for all loops from the triplet up to the 27. And this is true both with pure loop and with quarks. It breaks down in the low temperature region, but away from there, it is approximately.
I think this is really, I know these results, but this is always surprising me as this larger than unity, okay? Because if I have a Polyakov loop in different representations, okay, there is completely different physics behind. I mean, because if I have a singlet or color object, okay, in the confined phase, I can have different screening properties. So that's why I would expect that this coincidence is really surprising by the scale.
I completely agree.
Potential is also different. I mean, this potential has been calculated between Polyakov loop in different representations, and it's really different.
In the confined.
Yes,
Absolutely.
very different.
But this is what the data tells us.
Yeah, I know, but this could maybe indicate that this renormalization is still not well under control. I say it very loudly because I'm afraid of my friends from Ladis.
Okay, I think, however, that there are at least 2 methods of renormalization that have been developed, one by Bielefeld and one by myself and collaborators. And one of the things of this work by Kaczmarek and collaborators is that when you do it correctly, they agree completely.
Okay.
I think that's a fair statement, Olaf.
Yeah, that's a fair statement. Furthermore, people calculate Polyakov loop also in correlation theory, and there they see this kind of scaling at least up to, I think, 3 or 4 loop order. It must break down at some higher order, I think.
Yeah, I actually, since you mentioned this, the scaling of the Casimir is similar to that. You can consider a Wilson line at 0 temperature that has a kink in it. This is related to the Isger-Wise function. And people have shown that you have a similar scaling of that anomalous dimension by the Casimir up to, I believe, g to the 6. It's not known if that's true to arbitrary loop order, but this kind of scaling suggests that it's at least true.
I mean,
At least up to order g to the 6. I believe the same kind of proof would carry through. It doesn't mean it's true to arbitrary loop order.
in the high temperature phase, in the perturbative regime, I can eventually understand it, okay? But the problem is, which I have, is in the low temperature, in the confined phase.
Oh, I'm not making a statement about the confined phase. This is only.
Then I would expect that there is a very different physics if I have a Polyakov loop in different representations. Because potentially.
Well, there certainly is, if you can consider 2-point functions.
Look, if I have an octet, okay, then I can produce a singlet states with surrounding particles, when I have a fundamental, I cannot.
Nevertheless, as Olaf and collaborators showed, for states that are Z3 neutral, such as the adjoint, the expectation value of a single loop is very small in the confounded phase. That is surprising. And in fact, that suggests, yeah, that's crazy.
Can this scaling be perhaps understood from the Lagrange limits?
Yeah, and larger, actually, this just becomes some trivial factor of an integer. And in fact, my collaborators and I originally suggested this, and if I can say, Olaf came up to me at some conference and said, "You're wrong."
Very good.
And he said, "Yes, you're wrong. It's not just by an integer. If you scale it by the Casimir, it's an identity. All these curves fall on top of one another." And if you'll excuse me, Olaf, I don't think we were really wrong. But this is a point that you can ask him about.
Rob, you
But
are
yeah,
never
at large end, this Casimir is just a factor of, I believe it's like 2 for the adjoint versus 1 for the fundamental.
Rob, you know that you are never wrong. You are almost correct.
As long as you're not boring, right? You know, wrong is fine. Wrong is fine. As long as you're not obviously wrong. Obviously wrong is a problem. You don't want to be boring. Are there any comments claiming that I'm obviously wrong? No? Okay. Okay, let me then go on to make some comments about a pure gauge theory. I'm clearly not going to finish my lecture, but I think it's okay. Because it's another thing that I want experimentalists here to remember, because there's a lot I understand. An example of constant Q is kind of like, oh, please. Well, you've seen many times the plot of the interaction measure, the energy density minus 2 times the pressure divided by p to the 4th. This is a dimensionless quantity. It is a big peak. This is now for the pure gauge. And then it falls off. And this is data from Borsanian people and pure gauge. And you can ask, well, what is this tail here? Well, the tail you can show has a very simple interpretation. You can ask, what are the leading corrections to the ideal gas term? Well, turbulent G squared, G cubed, G to the 4th. But the leading power law correction near TC is just a factor of T squared. And you can show this by plotting e to the minus 3p over T squared. To get the dimensions right, you have to include the confining temperature. And this is approximately flat. Eventually it goes up because of the conformal anomaly. But over a large region, it's approximately flat. And in fact, so one mnemonic for the pressure in pure gauge is just a T to the 4th minus 1 times T squared times the confining temperature squared. And this constant must be near 1 because we know the pressure is very small in the deconfined phase. And then, now you might say, oh, well, this is just some kind of gluon mass term. We get T to the 4th minus mass squared times T squared. That's all it is. That's trivial. That's obvious. But there's lattice results by the Italian group, Casale and collaborators, in particular Michele Pinero, which you show that in 2 plus 1, where the ideal gas is T cubed, that again you get T squared. And if there was a mass term, it would be n squared times T, not T squared. And so what I would argue is that this is due to the pressure of deconfined strings. And the reason why I say it's strings is just because it's T squared here and T squared there. But for the present purposes, all you need to know is that the leading correction is T squared. And so, in the time remaining, what I'm going to tell you briefly about, there's a matrix model for a pure gauge theory, and I'll now introduce the other diagonal matrix that Professor Reinhardt asked me about, which is 1 minus 1, 0, as well as the other matrix that is related to Z3 transformations. And we're going to consider paths in this direction, in this T3. And the reason I do that is because now instead of splitting things like before, I'm going to have one root along one, and then the other two roots are along either the plus or minus 2 pi over 3. And when I do this, what you can show is that I can take a path that goes from the perturbative vacuum when q equals 0, and if I go to q equals 1 with this normalization, one can show that things open up, and I get the previous, at q equals 1, I get that, and I get the confining vacuum. So it's clearly a path to go from the perturbative vacuum to the non-perturbative. And in fact, what you can show, remember that potential I derived, that's why I went through it, that you get a potential like that of q squared times 1 minus q squared, and the perturbative, from perturbative fluctuations. Here's the pressure of an ideal gas of gluons. And then we're going to add to this a non-perturbative potential proportional to t squared. Now, I'm going to take various terms, and I should say this is just something that we're mocking up. We're throwing this in by hand. We have no derivation. It must come from some sort of fluctuations that are manifestly non-perturbative. We take a term, you have to take a term that's, you have to satisfy various symmetries. This is define absolute values of difference of these q's. These q's are these different elements here. You have to define them to be absolute value modulo 1, and I could go through that. But we add a term like this so that there's always a little bit, you're always a little bit in a semi-QGP where Q is non-zero. Simply because it starts out like a linear term. We add another term that's like the perturbative with some coefficient, and we take the whole thing proportional by the t squared. Now, without going into the details, what you can see is, remember, from the data, that most of this is 1 over t squared. It's a constant. So if we take out this t squared, everything that's left is going to be concentrated in a narrow region around the deconfining temperature. And so what's going to happen is that we're going to get a narrow transition. And we also had a model with a bad constant, but that doesn't really change things. The point is that you do this and we get results that are within. So we're just choosing two constants, we're fitting to a function, so it's not really, it's just curve fitting. And this is where you compare to lattice data on the latent heat as well, comparing to Karpacz collaborators and data. But again, in most of this region, this is just coming from this constant here. Minus q squared. We can then compare to the results for the interface tension. This is results for both 3 colors and 2 colors. Here, this is the interface tension I computed perturbatively, semi-classically. This value is now computed using this complete effective Lagrangian. It's a straightforward exercise to do so. You have to do so numerically. You can't find the semi-classical solution so easily, but when we compare to the lattice data, which exists for 2 colors, we get a very good result. In particular, it differs significantly from the semi-classical, particularly as you get near the transition point. On the other hand, when we compute the renormalized Polyakov loop, we find a result that's in complete disagreement. So this is the results with our model, and as I said, this is from the transition temperature to 50% above, and it goes quickly up, no matter what kind of parameterization we take. The lattice is much broader. So we have a model where we fit to the Polyakov loop. It agrees with the interface tension. It agrees with the pressure. The pressure was a fit, so that's not really a test. But the fundamental parameter that we are trying to fit is in stark disagreement. And it's something that well, you'll see in the theory with dynamical quarks is even harder to understand. That this, what I want to stress is that this result for the normalized polycouple, which is a very broad transition from 0 to 4 times the deconfining temperature, is not true in our model. And you'll see this is true as well in the model that Professor Reinhardt will talk about. Okay, how many minutes do I have now?
5.
Okay, in the time remaining, I was going to tell you about something called bird track diagrams, but I don't have time to do that now. I'll simply tell you that I'll flash through that it's a trick due to Penrose originally, and there's a very nice online text by Karpacz, and it's basically for the theories. If you need to understand how to compute any group theory diagram, you can do so without knowing anything except one projector. All you need to know is this projector. But given the time, let me tell you about work which I did is somewhat different, and that is that you can solve these theories at infinite n. For reasons of time, let me simply show you. This goes back to you can put the theory on a femtosphere, and remember I said for a first order transition you always have a barrier between the two. And infinite n in particular models that I won't go into, this is what the potential looks like at the transition. This is the x-axis is the polycouple, the y-axis is the potential. The value jumps from 0 in the confined phase to 1/2 in the deconfined phase, but there's no barrier. If the transition is first order, and you compute the energy density, it jumps. The order parameter jumps, but there's no barrier. It's absolutely bizarre. And in fact, you can take the model that we solved, and this is something that I did with Vladimir Skokov, and in fact, I should say that the solution of the model was first obtained by him. So you can take this model, this is this V1 and V2, and the models we had before, you can write it in terms of various, deal with random matrix models, are familiar with eigenvalue densities. And what you can show is that, and in fact we've shown recently with Hiromichi Nishimura, that it's true for a wide class of models, much broader than we originally thought, that at the deconfining temperature you have universal eigenvalue density, which is equivalent to that in several different models, and we suggest maybe universal. And in fact, we suggest that it could be the solution for SU infinity. This is in the pure gauge. The question is, how large does n have to be? This is a plot then of the potential. Remember again, I said that for a first order transition, you have a barrier between the two degenerate minima. So this black line is the barrier in our matrix model. This is the confined phase. This is the deconfined phase. This is n equals 5. Let's look at n equals 19. It goes here. There's your barrier. It goes up again. And we're always rescaling by the number of degrees of freedom. And what happens is, as the number of colors gets bigger and bigger, this barrier gets smaller and smaller and smaller and smaller, until at infinite n it's absolutely flat. And the reason why it has this bizarre behavior is because at infinite n you can get funny things going on in matrix models. The way of seeing this would be to look at the interface tension because of the reasons of time. I won't go into this. There's a lattice data that suggests that the interface tension might vanish at infinite n. Unfortunately, it does so relatively slowly. And so you'd have to look at rather large N, at least 20 or so, in order to see this phenomenon. But it suggests that, as one might think of a pure gauge theory, that there are surprises going on, even without dynamical quarks in the limit of infinite N. And with that, I'll stop. Thank you.
So we already had quite a lively discussion, but any further questions, especially from any students? Jakub, any insightful question?
Or stupid questions. I welcome
Exactly.
stupid questions that are easy to
The
answer.
stupid one I had. You showed in the previous slide, you showed the potential.
Potentials as a function of n. So the black line is way more symmetric than the other lines. Is there a deep reason behind?
I've never noticed that. I have no idea.
But the strength of the transition,
It must reflect the mass square.
the strength of the transition depends on n. The strength of the transition depends on n, so this gap at PC will be n dependent. Number of color dependent.
No, what's weird is that the first order transition, the strength of the first order is not vanishing at infinite n. It's proportional to n squared.
Yes.
What this is showing is that the curvature of the potential is related to the mass. So in this case, this mass squared is going to 0. Yeah, what I didn't explain. Okay, no, I think I can explain. If you look at, there's a mass squared around here, which is the curvature of the potential. So that was vanished because it's flat. The curvature here is non-zero. So that mass squared is non-zero. It's small but non-zero. And that must be related to y. See, this curvature is, yeah, it must be, this is becoming flatter and flatter. But this, what's going to happen is it's going to go up, and then there's always going to be a sharp discontinuity because it has to be continuous. So it must be related to the discontinuity in the mass squared about each potential. That was the point.
Good. Any further questions? Oh,
Bob has some comment.
Well, I would have one quick one here. So if you calculate, instead look at V as a function of Q, and look at the curvature, as you said in last scale, that would be related to somehow to the curvature here, which would be related to susceptibility actually, the fluctuations of the potential. So how would this change with temperature? Have you looked at this?
We haven't computed this.
But it's a curvature simply.
I would like to come back to your analogy between confinement and understand localization.
Yeah.
The picture you gave is fine for a quad, if I understood correctly, because it's sensitive to the phase of the domain, but such a quad is insensitive to that. So, is there any analogy you can draw?
I think therefore, the fact that perhaps another way of stating your question is why is the expectation value of the adjoint loop so small in the confined phase? If you just look at the Z3 symmetry, there's no reason why it should be small. And I think there, the simplest way of understanding it is if it's based upon some matrix model. In a matrix model, if you have a completely flat eigenvalue distribution, the expectation value of any loop will vanish by group theory, irrespective of the Zn symmetry. And so that's the strongest argument I would have, that there must be some underlying matrix model that describes the confining deconfining. Excuse me?
Then the analogy doesn't go beyond the standard investment.
Yeah. That was just meant to be an illustrative picture. But it's a nice picture.
Yes.
good. Unfortunately, we don't have time for any further discussion, so let's thank Rob again. And we'll have 8 minutes break.